Welcome to Point Free or Die. Tacit programming in Haskell and beyond. All right, so what is this thing? Point free. Our point free is a style of writing function definitions. A point free expression is a kind of function definition. But point free is kind of bigger than that. It's a way of talking about transformations that emphasizes the space instead of the individual points that make up the space. So what's this other thing? Tacit. All right, so tacit is just a synonym for quiet. And tacit code is quieter than noisy code. And here's an example of a point-free definition down here at the bottom, and its point-full counterpart. So both of these definitions describe the same function. It's the sum function. And you could say the first one sort of reads like this. To take the sum of a list of things, do a right fold over that list, starting at 0 and using addition to combine items. Or you could just say, sum is a right fold, using addition, starting at 0. All right, so why would you want to use the point-free definition? What's the point of removing all of these arguments from your, I didn't mean to do that, from your functions? All right, so it's really simple. I'm going to say there's two rules, but I haven't even put them on the slide, so never mind. Point-free style is a tool for tacitness. And tacitness is just a tool for communication. So that means that when you want to make your code communicate better, you can use tacitness, and you can use point-free style to make it quiet. Why would you want to do that? One reason is that tacit code can keep you talking at the right level of abstraction, so that you're not constantly switching between low-level and high-level constructions. Well, here's another example. All right, so lengths, pretty useless function if you ask me, really. But lengths can take a list of lists and map the length function over that list of lists. Or you could just say lengths is a map of length. All right, so point-free definitions are a way that you can be more expressive with your code. So here's one more example. All right, so here's a function, total number of a list of lists. To get the total number of the items in my sublists, I want to take the lengths of all my sublists, and then I want to add all those together. Or I could just say the total number is a composition of sum and lengths. So I can use the composition operator right here. And then you might say something like, but point free has more points. OK, so that little dot, it's not a point. It's composition. And you're better off thinking of it as a pipe. If I have two functions, outside and inside, their composition works like this. Their composition is a function that takes an argument, applies inside, and then applies outside. I can do some Haskell magic here. I can use the $sign operator here instead of parentheses, which means the same thing, essentially, that I want to do this part first and then that part. And I can squeeze out the toothpaste here, I like to say, and I can move my $sign to the end here and replace it with composition. Of course, when I have a lambda abstraction that takes an argument and does nothing but applies a function to that argument, then I don't even need the lambda abstraction. So you can read this as outside composed with inside. That's probably the best way to read it if you want to remember that it's a composition. All right, so why? Or, sorry, I already said that. All right, so when should you use a point-free definition? Because you can use definitions that aren't point-free, and you can use some that are. And here are my two rules, which are really just one rule. Use it when it's good, and don't use it when it's bad. OK. All right, so this was the definition that we came up with. Total number is a composition of sum and a map of length. I decided to ditch lengths. And this is a point-free definition. But if you ask me, this is kind of another useless function, because for one, it doesn't communicate a lot more. Total number doesn't communicate a lot more than the composition of sum and map length. Really, if you think about it, I'm mapping lengths and then I'm adding them up. That kind of gets across the idea. And another problem is that, like, if we take the total number of a bunch of sublists, that's like one way that we can summarize all the sublists. But it's not the only way. We might decide that we want the total max. Like we want the maximum value in each sublist. We want to add those together. Or we might want the number of items in each sublist that meet some criteria. And we'll get the total match by adding them all together at the end. So One thing I really like about functional programming is that it encourages you to think in a general way about problems, whereas my experience with object-oriented and dynamically typed object-oriented code is that it really encourages you to do the opposite. It encourages you to say things like, you ain't going to need it, so don't bother thinking about the case that you haven't actually started to use yet. Functional programming, on the other hand, because you're using pure functions, you're restricting side effects, you can use wholemeal programming, where you think in the broad, think about when the general constraint applies, and then you can narrow it down to the specific. So to see an example of that, let's extract a little helper here. The total number is the sum composed with a map of length, but it's also just a way of aggregating these sublists. And we're aggregating here using length. We could aggregate using another function. Aggregate here is actually a local helper function. And its definition here is a composition of a sum and the map of that metric, which I'm calling f. And you look at this and you actually think this is not a point-free definition, because I've got an argument over here. But it's not really a point-full definition either, because what it returns is a function. This thing is the result of doing this thing. One result is total number. So total number is a function here. So we can see all of the arguments by using a process called eta-abstraction. Eta-abstraction looks a little like this. All right, so there's a missing argument here, or there's a hidden argument, a tacit argument. We can add it by applying this quantity to the new argument. And then we can unsqueeze our toothpaste here. And then, of course, we can go back to the way that normal, sane people write, parentheses. All right. So you saw eta-abstraction, but the trick here is that that definition of aggregate that we saw, this one down up here at the top, it's also not point-free. So we can make it point-free. We can remove arguments with eta-reduction, which is the opposite of eta-abstraction. All right, so this looks complicated, but I'm going to walk you through this. All right, so we have aggregate f, and it's the composition of sum and map f. Composition, remember, is just a function. It's being used here in an infix notation, but it could just as easily be used in a prefix notation. So we'll just do that. Now over here, I just have the parentheses here, and I'm trading it for a $sign. It just means that I want to do this first, and then I want to apply this function afterwards. I can squeeze out that toothpaste here and make this a composition and apply this at the end. And now, just to show that I don't really want this argument anymore, I'll just switch it over here and write this as an anonymous function, like a lambda abstraction here, with the argument starting here. And that's the only thing that changes here. And because I have a lambda that starts with an argument and doesn't do anything but apply a function, I don't even need that argument. I don't need to write a lambda. So I've got the composition here of this thing and map. And I can just write that infix as kind of it's called a section. So I've got half of the composition of sum composed with map. Well, that's great. That makes a lot of sense, right? I mean, that's easy to read, it's easy to understand. All right. So we have these two things. We have this not point-free and not point-full definition. And we have this one that's completely point-free. And you're already probably thinking, this is terrible because I don't know what this thing is. I don't even know how to say it. So let's look at it a little more closely. It's a function that takes two functions, f and g, and it composes them in a weird way. It combines them, not quite composing them. It composes this part with that, and that thing's like half of a composition. All right, so this thing, we can eta-abstract this thing so that it looks a little bit better. And you don't have to go through all these steps. Just take my word for it. You can see the x filtering in here, and then I realize I can add a y too, and I end up with this down at the bottom. And what I have is a pipe. I have a function here that takes two arguments, one argument after another, and then it applies another function to the result. So this thing is a combinator. A combinator. It's a lambda expression that refers only to its arguments. There's nothing that it does that isn't here. The only stuff that it does that isn't here is part of the system, the the application of a function. So it's a combinator. Here's some examples of combinators. We have this one, the one that we're currently investigating. This one up here is composition, the one you've already seen, because it just applies g to x, and then f to the result. And these things that you've also seen are not combinators, because they make reference to items, objects that are not here in the argument list. So we have our combinator. And it turns out that this combinator has a name. It's the blackbird. All right, so where's that name come from? This is Raymond Smullyan. He is, perhaps was, he is a professor of philosophy and logic. And he wrote a puzzle book, a logic puzzle book, To Mock a Mockingbird and Other Logic Puzzles, an amazing adventure in combinatoric logic. So basically, it takes you on a tour of the forest. You get to meet a lot of birds. And the birds say different things when you tell them the names of other birds. And this bird is a blackbird. All right. So here's our blackbird. I decided to go ahead and give it a name. I'm going to give it a name, ... And it looks like this. If you can apply an infix here, f ... g, f blackbird g, or the blackbird of f and g, it means that. And I can eta-reduce again, and this is just the same distance that we already traveled. And we can get back from this expression back to this one. It's a pipe with two inputs. You know what? It turns out that this isn't, since this isn't a point-free expression, I can go ahead and write a point-free definition of blackbird if you want to see it. So this is crazy. The blackbird is the composition of composition and composition. All right, so we have a new way to write our function aggregate. It's the blackbird of sum and map. Now, I'm actually serious here. Like, I don't think that this is a joke. I think this is great, because just like, hear me out. This is great, because just like how composition is not a thing that we think about. Like, it's not like when I try to understand composition, I go back to the Latin words and I tell, oh, it's the com of the posing. Like, instead, I'm just like, composition is a pattern that I'm familiar with. I see it, and I become familiar with it. Blackbird is a pattern that you can also become familiar with. You can remember, to start off, that it's a pipe that takes two inputs. Takes the two inputs, and then it applies a function, and then it applies another function. But after a while, you just remember that it's blackbird. All right. So I want to give you an example. I apologize, this example is a little bit mathy, but it's like the kind of math that if you forgot it, that's totally fine, but it's like, it's very early from your math education. All right, so you might remember the Pythagorean theorem and a squared, b squared, c squared, right? So there's the distance from the origin to a point defined by a vector. You just square up the sides and take the square root. But that's not the only way that you can measure distance. I mean, you know, if you wanted to tell me how to get to some other part of this city, I wouldn't care so much what the crow fly's distance is. I want to know a distance that's more like this. How many blocks do I have to walk to get there? And to get that, you just add up the absolute values of the components in your vector. So, so what if we wanted to work with n-dimensional distance? You know, like say we're talking about big data and we're talking about vectors in space and how close these vectors might be to each other. Well, then we might use coordinates in a list instead of just two of them. All right, so with a couple of helper functions here, we can go ahead and write these definitions. Like, here's the square, here's a square root, and here's an absolute value. And so we're aggregating squares and then taking the square root to get the Euclidean distance. And we're just aggregating absolute values to get the Manhattan distance. Of course, we can run these through the console. And we get some. We can, for one, we can sanity check here. This is a little further distance than a Euclidean distance. But there's something here between these two definitions that's like trying to get out. There's something they have in common that that maybe we can extract, and then we can understand distance a little bit better as a general case. So let's try that. What's happening here? We aggregate an inner function, and then we apply an outer function. So here we aggregate square, and we apply the result square root. Here we aggregate absolute value, and well, it doesn't really fit the pattern. Like, something's missing here. We don't do anything here. But it turns out that not doing anything is also a function. So now we have these in the same form. That means that we can actually write a definition that we can use to derive these. And here it is. Distance, outer, inner is the O composed of the aggregate of I. And so these point-free definitions here, generalized distance, or they are special cases of a generalized distance. All right, so there's an example. But you notice that like distance OI equals O composed with aggregate I, that this is not a point-free definition, right? Well, we can look at a couple point-free definitions, or we can look at one in particular. You'll eventually get here with eta-reduction. But of course, if you know about the blackbird, then you'll get here, which is not as ugly. But still, it's not really good. Honestly, it's not good. Because what does half a blackbird mean? That's half a blackbird of aggregate? I don't know. This definition isn't bad, but it only mentions the O and not the I. And you kind of think of these functions when you're talking about distance as like they're on the same plane of importance. So I would stick with this second one here. And I wouldn't go to the pointful definition, because I don't want to have to talk about the coordinates if I'm talking about the distance. All right, so tacit programming is not an all or nothing thing. And of course, I tricked you all to come here by giving you an extremely fanatical title. You're not going to die. You should use just enough tacitness to communicate better. And sometimes often you'll find that the partially point-free definition is the one that you like the best. So you should learn to do eta-reduction by hand, eta-reduction and eta-abstraction. You can find tools to do it for you because it's completely mechanical. So you can let the computer do it, but the result that you get might not be useful to you. So it's worth it to learn how to do this really mechanical kind of algebra. All right. Now, I've been showing you examples in Haskell. Point-free isn't really about Haskell. It's just a concept. It's easy to do in Haskell and F# and OCaml, I've heard. You can jump through some hoops and do it in Clojure and Elixir. I don't know any of those languages, to be honest. So I'm going to show you one that I do know, one that I get paid to know. So, all right, so let's see some point-free Ruby, right? All right, so if you know some Ruby, this might make sense to you. Otherwise, you can ignore it. I'm monkey patching proc. All right. Basically, Ruby doesn't, to have first-class functions in Ruby, you have to use an object, an instance of a class called proc. And you can make these literal procs this way. But otherwise, you don't really have first-class functions. You can't pass methods around, or you can't pass functions around. So I'm monkey patching proc here so that actually calling a function is going to be less noisy. And I also actually defined compose, so I'm monkey patching that too. And you can see these examples. I have a function here, that anonymous function that I've given a name, +1, and adds 1 to something. I have another one that times 10. If I plus 1 of 2, I get 3. If I times 10 of 3, I get 30. If I make a pipe out of those two and then apply 2 to it, I get 30. So let's see what compose looks like. Here's compose. And of course, blackbird is the composition of composition and composition. And we have aggregate as well. And these are all definitions that you've already seen. So I'm not going to spend a lot of time on them. And we can have all of those versions of distance as well. These are all the same function. They do the same thing. I didn't write tests to verify that, but. So the most pointful one looks like this. I take an outer function, an inner function, and a list of coordinates, and then I have to aggregate the inner function over the list of coordinates and then perform the outer transformation. And these definitions are just like the ones that you saw in that list. But why are they so noisy? Like, why are they so messy? Just a reminder, in Haskell it looks like this. And in Ruby it's looking like this. So the reason has to do with something called currying. All right? Something that you may know if you know Haskell is that a Haskell function, any Haskell function only receives one argument. And if you don't know Haskell, I probably sound like I'm crazy because I just showed you a bunch of functions that have more than one argument. But in Haskell, functions are automatically curried. So an expression that looks like this, take x, y, and z, and then do something, return something, actually is this. Take x and return a function that can take y and return a function that can take z and then return you some value. So Haskell makes eta-reduction easy by automatically currying all of its functions. Because when you eta-reduce, you're removing one argument at a time. All right, so I discovered point-free notation, I think, just a few months after I kind of got into Haskell, and I got really excited by it, and I kind of went overboard with it. And I was doing some problems, some exercises involving the game of Mastermind. So if you want a little refresher, game of Mastermind looks like this. Many fun hours I'm sure you spent with your hated siblings. So there's a code breaker and a code maker. The code maker has a secret code. It's made of pegs, and they're in colors. And the code breaker is trying to guess that code. And every time that code breaker guesses a code, they get feedback. That is, you have this many exact matches. You have this many pegs in the exact right spot and the right color. And you have this many color matches, which are like the right color, but who knows what spot. So I have a couple of definitions. I did have a couple of definitions in my exercises. This was for a CIS 194 course you can just find online and do if you like. And let's look at what I had for exact matches. So I pulled it up. Oh, sorry. Well, I'm actually going to walk you through exact matches first. All right, so say this is my code. Or say this is the code. And this is my guess against that code. Or how do I decide, how do I calculate how many exact matches I had? And this is fairly straightforward. We just need a pairwise comparison. We just go through, and these are the same. So this is, if we ask it, are these the same? The answer is yes, no, no, no. We add up the yeses, and we get 1. So 1 exact match. All right, so here's my definition for exact matches. All right, so don't try to parse this in your head. Just notice right away that this is a point-free definition. And notice also that I've got this little pattern here, which you might remember as the motivation behind naming a blackbird. So let's go ahead and fix that. All right, so now this is somewhat less noisy to look at. There's like less parentheses. It's sort of easier to see. And we have a blackbird of this pipe and zip with equals. So basically, I have a pipe that's like kind of in 2 parts, or you could think of it in 3 parts. I've got these 2 parts, and this part over here is also in 2 parts. And it takes 2 lists of pegs, zips them together with the equals comparison, filters the ones that pass the comparison where the value is true, and then takes the length of the result. So here's a comparison of those two functions. Now, it's my opinion that the one on the top communicates better, and maybe that's something that I might need to sell you on a little bit better. But a point-free definition here lets you stay at the level of abstraction where you're talking about transformations on lists. I have one transformation that brings 2 lists together. I have another transformation that filters out the ones that have the values that I like. I have a third transformation that counts up the values in it. All right, so let's go look at how I did with color matches. All right, so we're looking at my old exercises from not really that long ago. And this is a possible scenario here. Same scenario as before. So how do we decide whether how many color matches we have? All right? The first thing we need to do is that we need to ignore position because position doesn't matter anymore. We need to collect the pieces that are alike that we want to compare. So we can run both of these codes through a function that changes the way they're structured. And we have something more like this. All right, so we've got reds over here, greens over here, and blues over here. And I've got 2 on both sides, so I've got 2 matches. I've got 1 over here and 2 over here, so I've only got 1 match. And here I've got 0 and 1, so I've got 0 matches. So it's 2 plus 1 is 3. So I have 3 color matches. All right, so here's some code that does that. All right, so this was the code that I attempted to pass off as code that is easy to understand and communicates what it intends to do, and it's objectively awful. And if you went to any presentation today where like someone told you that you can prove things with code, somebody please prove that that was awful. All right, so that didn't work. So let's go back to a fully pointful definition. All right. To get the color matches of two sets of pegs, two lists of pegs, what I want to do is I want to count the colors in each of them. I want to zip them together, taking the minimum of the values, the counts, and then I want to add up those counts together, just like we did on the slide a couple slides ago. But if you ask me, this really irks me that I have to say count colors twice here. Like I have this this transformation that kind of looks like this. I have these two lists, and they're coming together like this. And I have to do something here to put them together, and then I have to do something after I've done that. But then before I put them together, I actually have to run the same transformation on both of them. So I think something I didn't know when I was writing that old point-free definition was that there was a way around this that was much more elegant. In fact, I have this kind of problem involving combining functions. I wonder there might be a combinator for that, and there is. It's called the psi combinator, and it actually lives in Haskell. It lives in a module called data function, and it's called on. Now, here's the type of on. You can go to the console and see this. This looks a little scary if you're not used to it, but it's OK. This thing is a function. That thing is a function. And because this little bit is automatically curried, it's not presented in parentheses, but it's also a function too. So on takes a binary operator that takes two b's and makes them into a c. It also takes a function that transforms an a into a b. And it will give you back an operator that will take two a's and then give you a c as a result. So I can use it here. I can take the zip with min on count colors. And here I'm using an infix notation instead of a prefix notation. You could imagine on being here, but the backticks mean that I can put it in the middle. So this actually reads well, too. So if I count colors of both, I can zip with min them together. And I get a function that looks like this. Two lists of pegs, and they give me back a list of numbers. All right, so let's go ahead and try it out. All right. So now using on, I can do something like this. If I want the color matches of the two lists of pegs, I can zip with min on count colors, apply that to the list of pegs, and then get the sum. And of course, I don't need to use the dollar sign. I could use the parentheses instead. And of course, this might be even easier to communicate to people who are not familiar with Haskell. But if I'm looking at this, there's actually a pattern here that we've actually seen a few times. If I want to get rid of these, I wonder how I would do it. And it turns out it's not too hard. What I have here actually is a pipe of a function taking two inputs and then using an outer function. So I have a blackbird. All right. So here's the point-free definition of color matches that I think communicates very well. We want to zip with min on count colors, and we want to take that result and sum it. All right. So here are two functions that look alike. Now, see, here's the pointful version, the version that irked me, I guess. And here's the version that I came up with just by using eta-reduction with what I knew. And here's what we could do today. So when someone says to you, don't bother with point free, you're just going to end up with obfuscated code that's not worth it, remember that there's more than one way to do point free. There's more than one way to arrive at a point free definition. But what did we do differently? What was different here? Like, why did we come up with something that was better, cleaner, more elegant? And the difference was that we knew about on, and we knew about this way of composing things in a pipe that takes two inputs. So some advice. If you want to do point-free style, learn eta-reduction, because you want to be able to find the intermediate step that works best for your communication. And learn combinators so that you can use them. So when you see a pattern that comes up again and again, you'll be familiar with it. Because this is what we do when we learn to program. We learn to see patterns that come up again and again, and we learn to apply them. All right. So this is a guide to point-free without dying. Point-free is just a tool for communication. And Tacit code isn't better unless it communicates better. So point-free and die, point-free or die, the choice is yours. All right, so I wanted to say some things that are beyond. There's a lot of stuff that I said that I would get to that I didn't. Point-free style has a really long pedigree, has a long history, and it comes from conversations in computer science about how we could make programming and how we could make computing more composable, and how we could actually build abstractions that are concise and still don't leak. And that's something that we're still chasing today. And I know a lot of people will look at syntax, and point-free is all about questions of syntax. A lot of people will look at syntax and say, syntax is just not important. But I think nothing could be further from the truth. Syntax is where we communicate. And how we choose to communicate will make programming what it is for the days and years to come. Thanks. Looks like we have time for questions. Yeah. Question was, what if you have a function that takes 3 arguments? And the answer is, I leave that to the reader. All right. Any more questions? Yes? Do I consider, I've never thought, okay, the question is, do I consider lens operators point-free? I've never really thought about this. I think the question of whether they're point-free is a pretty easy one to answer. It's just the point-free is something to say about the implementation. So if you go back and look at the implementation and it has arguments written, then that's not a point-free definition. But if it doesn't, then it is a point-free definition. But I guess maybe the question could be more like, can you do point-free stuff? What? That's something I'll have to take home and think about. But thank you, because now I have more to think about. Any more questions? Okay, Dave.
So you've got all these recipes in your head. Like, you should clearly practice this. And you like see the blackbird, and it's like a language. And if I'm like, yeah, I want to do this, how do I practice this language? Like, just repeat it until I see it everywhere. And how do I communicate that with other people? How do we teach them this language?
Yeah, it's a great question. So the question is like, if you want to get to the point where you're used to seeing patterns and using them over and over again, like, well, how do you get to that point, and how do you communicate it to others? I think that, like, you know, there's more than one way to learn things, right? I mean, there's a way that's like you're going to go out and get a book about it and read it and learn it, and then or practice it until you learn it. And then there's also the way of like just doing things that are kind of in the same zone until you start to pick up the skills that sort of happen again and again. I think both are valid. If you want to learn combinators by going out and studying combinators, I'm planning to get through this logic puzzle book, The Mock a Mockingbird, and I would love to read it with some of you. If you just want to do exercises that help you get to know Haskell and get to know functional programming better, I think that these patterns are going to come up and you'll just become curious about them. Yeah? The title of the book is To Mock a Mockingbird. I believe the subtitle is And Puzzles in Combinatorial Logic or something like that. It's by Raymond Smulyan. All right, any more questions? Yeah. Yeah, well, I've heard people say things like syntax is not important, or let's not get into conversations about syntax. I think it might be like a sort of a defense mechanism against getting into arguments about syntax. Because it's easy to bike shed about something where there's no like clear answer. It's not clearly true that this definition is better than that one. I think I presented some definitions that maybe some of you didn't think were better than the counterparts. And so it's easy to get into an unending sort of conflict over like which one's better. And I think that some people avoid conversations about syntax just to avoid that. I think that the fact that we can't come up with a clear-cut answer about syntax indicates that it's very important, and that that syntax is a really, really important. It's where we have many strong feelings because it really matters. So yeah, I think syntax is important, but I don't pretend to say that there is one right way. All right. Well, thank you all for coming, and hope you enjoy the rest of Strange Loop.